ranging from, say, plugged culverts to hazardous sections of road. Standard prescriptions of the BMP sort are recommended, and general costs, therefore, can be tallied. What tools to use? A clipboard of forms and an odometer make a simple tool set. Paper forms are best used for low to moderate levels of detail or for a small set of sample sites. The main advantages of paper forms are low cost and no reliance on batteries. The drawbacks are that data entry becomes an extra step and quality control is poor. Here's an image of a data entry form off of a computer that is carried out in the field. Digital data entry forms are most useful for moderate to high level of detail. These are very functional for data management and analysis. These can be used in the field via portable devices. New options are rapidly developing. The main drawback is the need for batteries, which is a big concern on long deployments away from electricity. But the main advantage is a high quality control. A dual system of locating is recommended. Adding a GPS unit can greatly improve map making. However, where GPS signals are poor, the odometer remains a standard. Some cameras are equipped with GPS and come with software that makes captioning easy. This image illustrates captioning possibilities. Otherwise, the internal clocks in separate camera and GPS units can be synchronized to allow geotagging. In many map viewers, geotag photos are spatially linked and can be activated by simple clicks of the mouse. Here are some typical general-purpose tools used by field personnel during road assessments. The key interests are to accurately identify the location of observations and to measure some physical aspects of them. Custom equipment has been developed for specific purposes. Precise measurements in very limited areas can be extrapolated to broader homogeneous areas. This device collects sediment samples for lab tests such as grain size characterization. The desired products and outcomes of a road assessment determine which sort of methodology is best. The methodologies, along with the level of detail, determines which tools are best. There is a rich assortment of geographic data and viewers available to the public, ranging from the free to the expensive. They have different capabilities and are frequently upgraded. They provide linkages to existing spatial data sets. Utilize existing maps, data, photographs, and documents and other data to get a preview of the road system and of the landscape. These data sources provide background files that I often use during road assessments. Much important information can be gleaned from online sources. The following examples derived from the 3 data sources listed on the previous slide. You might want to view these examples in the full screen mode. National Map provides a viewer with multiple layers in addition to the standard topographic map, such as the hillshade and the stream flow lines seen in this image. On this image, I highlighted a road of interest. From this viewer, it was easy to pre-identify 11 watercourse crossings. These points can be loaded into a GPS unit and carried out into the field for help during the assessment. Small watercourses can be hidden in the brush and can be easily missed during assessments. By inspecting those crossings in Google Earth, a watercourse that diverts down the road is easily identified, as indicated by the blue line that diverts down the yellow line. This example illustrates the value of hydrography based on higher resolution elevation data. Using the previous approach identifies 3 crossings of an ephemeral stream. Unfortunately, USGS blue lines often underrepresent the drainage system, especially in arid or Mediterranean climates, such as this site in the Central Coast Ranges. By deriving a hydrography model from a 3-meter elevation model, 27 watercourses were identified. That's 9 times more. Models such as this are error-prone in headwaters and low gradient areas and require adjustments based on ground observations. Many of the sediment production models rely on this sort of synthetic hydrography. Field observations made during an assessment of watercourse crossings can help calibrate these models. LIDAR has many advantages. It can be processed to show the bare earth, roads and even trails, show through the vegetation on derivative images, as well does erosion features such as this gully. The entire footprint of a road can be captured. LIDAR is increasingly available, especially along the coastline. Downsized versions can be imported into viewers such as Google Earth. LIDAR has disadvantages of requiring complex processing and currently has limited geographic and temporal coverage. Roads are affected by landslides. Conversely, landslides can be affected by roads. Unstable slopes represent hazards for facilities and the need for geotechnical review and major sediment sources to streams. The impacts for roads can range from higher maintenance demands to complete destruction, depending on the degree of instability. The earthwork associated with road construction can reduce the stability of slopes and thus trigger or accelerate processes of erosion or mass wasting. A road assessment should point out that the road on the left crosses the head of a landslide, while the road on the right crosses above the landslide. Drainage from the roads into the landslides can promote instability and should be evaluated during an assessment. Would either of these road sections be considered reliable after a strong earthquake or a wet, rainy season? This road crosses the toe of a landslide. The road cut is likely to be very unstable. As the slide plows downhill, this section of road will require considerable effort to keep it open. It may be a candidate for decommissioning. However, it would be a poor candidate as an emergency route, especially during high rainfall or flooding. Note the blue line stream imported from the USGS 7.5-minute hydrography. The red line shows a truer course of the stream based on the underlying image. Hydrography based on derivatives of the standard 1 to 24,000 map lack sufficient detail for all applications. Hydrography based off of the LIDAR are much better. Less conspicuous landforms can easily be detected on bare earth LIDAR-derived imagery. The brown patches highlight gullied land receiving drainage from a set of switchbacks. Switchbacks can pose drainage problems. A road assessment should evaluate the relationship between the roads and the gullies. Also note the road is affected by stream erosion in the circled area. During floods, a streamside road is likely unreliable and possibly unsafe. I added some aerial photography. Let's look more closely at one of the switchbacks. The leadoff ditch extending from the switchback is dumping concentrated amounts of runoff into an unstable area. Here's one last example. Topo maps include information on sensitive resources such as springs. The bright colors are an overlay of the NDVI, Normalized Difference Vegetation Index, that show vegetation and soil moisture differences. The distribution of the bright colors of the NDVI implies a greater distribution of springs or seepage than does the simple blue dot of the topo map. A road assessment methodology that fails to identify the features noted in the preceding examples is missing valuable opportunities. Methods that provide detailed data about a culvert but overlook landscape level concerns may be overly focused. Determining the desired products and the outcomes and reviewing the existing information should provide guidance in the development of the appropriate methodology. What to collect data about? Beyond the preceding examples, this entire webinar series provides a substantial background to the important issues and concerns. Comprehensive methods would consider all of the topics discussed. Focused assessments would be limited to one or a few topics. In this webinar series, we have discussed 10 general topics, each with many details. The list of possible things to collect data about is quite long. Decisions as to what is important and the level of detail greatly affect the efficiency of a road assessment. The level of detail should be enough to satisfy the project's needs. Road assessments can be thought of as a phase one effort that guides follow-up phases. For example, an assessment may recommend that a section of road be reconstructed. The engineering details of those efforts are generally beyond the scope of an assessment. However, an assessment can provide a preliminary treatment plan that relies on standard prescriptions and BMPs. An assessment can rate problems from high to low severity and recommend specific treatments. That is, if and only if actionable data is collected. In this illustration, the mapping colors, red, yellow, and green, indicate different levels of severity, and the labels are similarly color-coded, and they say reconstruct dip or construct outslope, and those are BMPs, which are fully described elsewhere. The volume of data can be considerable for even a short road, let alone an entire transportation system. Usually a well-designed database is needed. We don't have time to discuss those details in this presentation, except to emphasize the need for unambiguous and structured terminology. Terms like rockfall can mean different things to different people. Both meanings may be applicable to a road assessment. A database search for the term rockfall could provide mixed results. Another example of the same word meaning different things, or even being pronounced differently, is slough or slough. Databases may not differentiate terms by their pronunciation. Common terms can be a problem, but so can uncommon things that lack clear names. What is this thing? Terms often need to be sorted into categories. The same term should not be used in more than one category. Terms need to mean the same thing to everyone. Data dictionaries are the way to clarify meanings. Addition of photographs to data dictionaries can be particularly helpful. Here's an example of structured terminology. Two categories that might be used in a condition assessment approach are features and their problems. The features category can have subcategories called feature type. Once you have a structured methodology, a data dictionary, a graph of concepts, and have previewed the existing data, you can begin a road assessment. Various methods will have various requirements for what to observe and how to record the observations. General examples follow to illustrate one approach. The buttons on the following screens represent categories and selections that can be made in a data entry form with a structured terminology. The following examples will illustrate a structured procedure for making observations. These examples are just a small sample of what might be encountered during a road assessment. Understanding the design of a road helps to direct and communicate observations. A cross-section perpendicular to the center line provides a convenient division of surfaces. Field conditions result from a history of events that are not precisely known during the assessment. Forensic interpretations can be inferred by considering how the various road surfaces interact as a system. A systematic approach that examines each of the components in the cross-section throughout a road segment will capture most of the necessary details to characterize a road. Many roads are either within or near high-energy dynamic environments such as unstable slopes, shorelines, or watercourses. Developing sustainable designs requires understanding the environment in which the road is intended to function. Recording the presence of landforms that are indicative of a risk environment is important for road assessments. Is the road within or adjacent to a floodplain? In cases of flooding, roads in or near floodplains are unsuitable as emergency routes. Evacuation plans need to have reliable routes. Does the road approach or cross a watercourse? Crossings must be able to pass all the flow and debris that a watercourse might deliver. Note the condition of any watercourses. Steep-walled and U-shaped channel profiles, exposed roots, and sliding banks indicate incision. Channels braid when the sediment load exceeds the stream transport capacity. Can the drainage structure in the background manage the surge of the material in the foreground of this picture? Whatever happens on the landscape ultimately will affect the road that crosses it. Cut slopes can remain as sediment sources for long periods of time. Chances of successful revegetation can be poor. On fill slopes, revegetation can be successful. Look for water emanating from the cut slope. Look for sediment production. Whatever happens on a cut slope usually ends up on the tread and affects drainage, such as blocking a ditch or causing ponding, as illustrated in these photographs. Unstable cut slopes are often a reflection of a larger scale instability, such as a landslide. Roads with unstable cut slopes are not reliable as emergency routes after earth discharge the water elsewhere. Examine the inlets and outlets of drainage structures to see if there are any problems. The condition of drainage structures can reduce their function. Problematic conditions gradually worsen over time, increasing the risk of eventual failure. Failed drainage structures often result in uncontrolled movement of water across road surfaces, such as the diversion shown in these photos. Here again is another cyclical dynamic where sediment clogs a drainage structure, the structures back up or overflow, causing sediment to accumulate in the channel. This reduces the channel capacity. Either heavy flows scour out and push the sediment down to more downline drainage structures, or the stream bed actually builds up and aggregation occurs, which makes flooding, localized flooding, more frequent in that area and deposition of sediment more frequent. And so the cycle can go on and on. Here are the 4 cycles put together. The interplay of the cut slopes, the tread surfaces, and the fill slopes and the drainage structures can lead to something like a systemic failure of the road system. Road assessments can help identify areas at risk and suggest interventions before stressing events or disasters strike. Failure is an option. Road assessments can help to diagnose and treat road-related problems and spare the landscape unnecessary impacts. Otherwise, cut slopes will ravel and rills will form on the tread. This starts immediately after construction, often. As this progresses, water can eventually pool in the tread and rills enlarge. The saturated fill eventually slumps and unstable cut slopes eventually fail. And things can get worse and costs can escalate to the point where you have sort of a loss of your road system.